Там у лосев курсовик стал. Можно ему оценку поставить. Вызову открыл эту ведомость. Что семерку можно наверное, поставить. Вот так. Так.
We walk. I need to do something here. I need something here. Come here. What's this? Fuse. 1,000 amp fuse. And what is characteristic of fuse? current interruption time. Like this. Good for fuse. Maybe even like this shorter. Usually they are drawn in logarithmic scale. Now question. We can create characteristic like this. Distance, time, what it will be in current time coordinates. In coordinates, current, time, 3 times, what we will have? 1, 1, 1. This first zone, this is time for the second, and this part is third zone. How this characteristic of simple overcurrent protection coordinates with fuse? What's your opinion? Not very good. Yes. If we have something like line at the end, fuse, transformer, fuse, it's better to have characteristic like this. First zone instant, second, and then third zone, something like this. We need to coordinate with fuse. It's better to have last zone, this one, zone what protects our customer connection with time 3 being function of current. Understood? This will allow us to coordinate with fuse. Also, click, circuit breaker. Circuit breaker. Where are you? Where is my nice old circuit breaker? Somewhere. Oh, I found one. Wait, there should be another one. No? What's this? I'm touching my finger with. This is old. Nice circuit breaker. Has instant. If you activate this, up, relay, it strips instantly. But it also has these two, where am I? Here, this and this two. This one with 2 elements. I need one more. Where's mine? Who is? a circuit breaker. This circuit breaker. Oh, here he is. Oh shit. What's this elements? 1, 2, 3, 1, 2, 3. Huh? Here I have instant trip, and this are thermal elements. Why is I needed? Why all this circuit breaker? Oh, here it is. Thermal element heater around bimetallic plate. It's made of two different metals welded together. If you heat it, it bends. Why these elements are needed? Why these low voltage circuit breakers to have these thermal elements? There should be some reason. What's the name of this device? Asynchronous machine. How will current works? Case startup current. In rush 3, 5, maybe 7. And this one is nominal current. This is operation current for instant part. Here I can adjust starting from 6 up to 10 of nominal current. If this one is market group B. Group B. What's the instant current of group B? Here, B. Yeah. Starting from 3 to 5. If it's rated 10 amps, group B. This means what instant it should trip from 30 to 50 amps. 3, 5. This one, it's an arrow. Five of nominal 25 amps. When it trips instantly, 5 multiplied by 25. So 125 amps. It's an instant. Actually, this one has an instant current. Can be selected starting from 1125. No, sorry. It's instant 1600. This one trips instantly at 1600 amps. Instant trip, 12 nominal current. More than group C. Typical group C, 8 to 10. This one 100% is for motors. So, up to 10, 12 of nominal current is a trip for the instant zone. But this will be not sensitive. To ensure sensitivity and to operate as an overload protection, thermal element, this one from 60s, this one manufactured somewhere in 50s. I have a tiny paper. Here. Don't manufacture. Wait, it's manufacture. No, it's operation. Manual. Don't have no, to my sadness, it's not manufacture. But I'm 100% sure it's manufactured in early 50s. And I have trip from 16 to 25 amps can be choose current for thermally protected. Thermal unit give you this. In high overloads your machine do not start. It trips fast. If you have normal startup process, it allows your machine to start up. If something goes wrong, I don't know, overload, it will trip. Now, you on a 10, 11, what is, use you on distribution network side. What? Thousand amps. This is guy you coordinating with, possible. Bit larger circuit breaker. Come to 1 floor above, you'll see kiloamp circuit breaker. You coordinate with it, and it has same type of characteristic, like this. You need to coordinate your protection, and kind of flat characteristic do not work well. What to do? Where to run? This one with the handle. If tripped. Here are thermal units. many people died, you know. See, it's strict. If you try to switch it on, not switch, many people died opening them. If you remove handle, this part is underwater. To push down and then push up. Disconnected. Don't see many short circuit in its life. Looks pristine. It's from Red Building, Faculty of Chemistry. They upgraded main switchboard, and I took this beauty. So where am I? I have problem. I need to coordinate this fuse with circuit breaker. You can find more expensive modern circuit breakers, low voltage, with characteristic like this. 3 straight lines. My flat characteristic not works well. It can, we can live with it, but it's not the best one. What to do? Solution. Here is old school solution for this problem called induction relay. Old school solution. I will remove the scale. So what's inside? Coil. Here. Coil with taps. I can choose which tap to use. This coil has a magnetic here. It's magnetic coil, and in the gap of coil we have this disc, aluminium disc. But the gap is not simple. See this? It's a kind of ring sitting on the coil. I can show it better. On this small fan, it's used the same technique. See these welded coils? Yeah. Here. Copper coils. They are called screens. Idea, part of magnetic flux goes directly and part through this coil. The part goes through this welded loop, induce a current in this loop. And its current has its own magnetic flux. As a result, flux going through this closed loop is delayed in relation to main flux. That means that flux in here, in pole, splits in two. And they induce currents in core, and these currents have their own magnetic flux, and flux of two fluxes, two opposite magnetics, result drag moment. This thing rotates. It's a fun from microwave oven. Screen pole motor. Here in relay use the same idea. Part of the flux induced by current of protected network goes through short circuit ring. This part is delayed. As a result, through the disk goes two fluxes with an angle approximately 45 degrees between them. They result rotation moment. This disk rotates. Second moment, the disk sits it can be shifted. Here also, this is magnet. Oh, here is magnet. This magnet, it's a braking magnet. It acts as a brake. So what happens? Rotation speed is dependent on current, but on small currents, disk is in retracted position and do not couple with this arm here. Toothed arm, and we have a spiral on the shaft of the disk. In small current, disk rotates without coupling with the arm. When current exceeds start up or pick up current when disk links like this with the toothed arm. Then disk rotation, wait 1 second. When disk rotates, it shifts arm up. And what's going on here? Oh, sorry. Arm like this. Shifts up. Yeah, shifts up. I also have, this is a trip indicator. Up, shows red flag. Arm shifts up and close this contact. So time to operate is dependent on current. The higher current, the faster rotates disk, and in shorter time, contact system closes. Here I may show. Here characteristics. With this regulator, I can choose zero position for the sectoral arm. So in coordinates, current, time, pick up, this is theoretical characteristic of tree. Only a disk, but that's not all. Here is ability to adjust. On the opposite side, I will try to show, it's another magnetic branch. This relay, this second side magnetic branch trips instantly. Instant current can be chosen, here is the scale, from 2 to 8 of pickup current. At this moment, it goes instantly. This point can be chosen 2 to 8 or startup current. So this old dinosaurs offers us two zones. One instant for line protection non-clearing dinosaur. Here in Riga, in some transformer substations, they are still in use. Because do not need batteries and do not require heating. Digital relays don't like to stay in unheated place. Yeah, this is nice. Modern relays offer us, usually good modern relays, offer us one or two time-dependent zones to coordinate with fuses and circuit breakers. Important moment. Okay, I'll draw transformer. Your line, here let's say 10 or 11 kilovolt, 110 kilovolts, 10 kilovolt fuse, delta, star, I don't know, 1000 to 2000 amp fuse. Customers. One tiny moment. Here is your relay protection device. Where to look? At a first good idea, appears to be good idea to create something like hole. It's in distance time. And this part should protect, let's say AB. It will be protected by B1, and this part appears to should coordinate with this fuse. Yes? Harsh reality. These fuses are unreliable. 10, 11 kilovolt fuses are not precise and often be prepared. They do not hold characteristics. They often are mounted openly and can lose their water tightness. Sometimes they filled with water, sometimes they simple linemen put what they found, not what needed. Abandon this fuse. Coordinate with this one. Simply, your life will be better if you simple look at low voltage. Sounds like kind of, okay, I will not use the word blasphemy, but believe in experience. Fuses on high voltage sides of transformers are not reliable. Coordinate with this one. Now, you need what? You can draw a line like this, or like this, or like this. Note, there is standard. It's named BS142. It has an IIC version, but everyone in our business watch on BS1.2. It sets time function of current. One second. First I need more chalk. table. BS 142 sets four main types of characteristics. Time in seconds equals to time multiplier beta divided E against pickup current in power of -1. Here is a common formula for BS 1.2. Standard defines four basic types of characteristics. When you create your protection, you need to do what? Start from the your biggest, most powerful customer and get information what kind of fuses or circuit breaker they use. In depends of characteristic they have, you will need to choose from normal, inverse, very inverse, extremely inverse, and a long time inverse. For these characteristics, you have alphabet. Standard, you can play with time multiplier. Time multiplier allows you to shift characteristics. But basic needs to correspond. Old time people know what old school. They have them on transparent paper and just find better fit. Modern days, you can use some spreadsheet like Excel, create your own set of characteristics. Like, for example, this one, it's independent of time multiplier. These are extremely inverse. You need such set of characteristics. And what you do with it? You take description of fuse link. First start with your top connection. And with description of fuse link, wait, where are you? Oh, here is correct. You need this one. It's guaranteed disconnection time as a function of current. Compare these two. See? Good fuses are extremely. You see them? So you have set of four characteristics. Extremely inverse, very inverse, long time. long time, fast characteristics are for good fuses. Long time for bad fuses. Go to rural area, I know the Indian type of fuse, only no fuse at all. Piece of wire from overhead line. For this long time. Okay, so choose correct for. Start from biggest customer. What kind of fuse or circuit breaker they installed? This determines what kind of characteristic you need to choose. Digits, alpha and beta, 1 second. 2 hundredths, 14 in 100, 1, 13 and 1/2, 2, 80 and last one, 120. Here are numbers for each type of characteristics. Also, remember there is a gap. Some manufacturers show it, some not. To understand, not most precise relay, but tolerances. Normal, very extremely long time. This is current relatable to pickup 2.22 of basic tolerance usually is for modern relays 5%. 234, 240. For small overcurrents, relays are not so precise. To comparison, for 10, 101 epsilon, 101, 102 epsilon. At small currents, many relays do lose precision. Take care about it, left sufficient safety margins. Okay, one more moment. If you deal with network where part of the relays are old, these old induction relays, to coordinate with induction relays, they are not fit into DS142. For coordination with induction relays, special Li type of characteristic should be used. Yes, it's given. For this type of characteristic, trip time in seconds is time multiplier. You can choose it. You can shift characteristic with, here is set of characteristics. You can shift them up and down with the help of time multiplier. time, so for array type of characteristic, time multiplier divides by 0,339 minus 0,236 current EP cup. This is array. Some relays do have RxIG characteristic. This is for Earth fault protection. Do not use it for, it's not good for ordinary max current protection. Do not use it for Earth fault special. It goes in opposite direction. Yeah. Time dependent characteristics. With if you have, for example, A, B, and fuse protected C, this is important chart called selectivity card. It has its name. It's a selectivity chart. It's time of disconnection as a function of current, usually drawn in logarithmic scale. What you need to create a selectivity chart? One. Line. Max external current for line B. 2. Max external current for first line. Max external. Max external. Show them on your chart as vertical lines. This is 1. This is, for example, 2. Max external currents. What will be and yellow line, this one should be 3. Wait one moment. What I'm doing? Here should be 3. Sorry. It's stupid. Okay. When protection A trips instantly. A1. What's the gap here? 10%. This one is a trip current for A. Where is the trip current for B? Again. B1. %, and maybe in yellow, this is C1. For A2, where's the trip current? magnetic current for A2 is 10% from this point. Draw plus 10%, 20%, and this will be all currents, let's say something like this. This is A2 and 1 delta T. B2. Now what? What should I draw? What will be B3? What's the determinant for B3? And maybe, okay, I will sequence this for A3 and B2. What I need to draw? This one. Instant. Okay. If instant, I will plant a circuit breaker here. Oh, if I draw instant zone, for higher current, it will become, look at the circuit breaker. Current time, thermal, electromagnetic, electromagnetic, thermal. It's an external, so I need blue one. I left myself no space. I will do it. Oops. This is number 3. This is instant C1. This is C1. And let's say tricky me. I will left a bit more space for myself. E max low R for C. You understand what I'm doing? This is fault current. This is max load current. Oops. This part, thermal part of C, I can mark it C2, but it's a thermal part of this circuit breaker. For fuse it will be, this would be fuse, simple like this. And now A3. A3, come here. A3. Maybe okay. I need to bit more. I have B1. Maybe like this. Will go B2. Oh, and now I will draw nicely. this will be A3. All should have, better have something like 20% of safety gap. You saw errors. Now it's fine. Here is my selectivity chart. B1, this point bit confusing. Oh, this one is better. Because I need to have, I just showing the safety gap. It should be only 10% because these are more precise, but I'll just draw it bigger. Actually, this gap should be at least 10%. Distance between these points is 20%. Oh. Looks a bit idiotic. That's what you will need to add to your project in real life. It's a selectivity chart. Selectivity chart with time-dependent characteristics. First, put external fault currents and max load current, and then you will be able to draw your nice, well-based characteristic. Okay, we'll eliminate this 20% and draw it here. 10%, 20%. Here is selectivity chart. And this line is in case of fuse. Good. Time-dependent characteristic is your saver when you need to coordinate with fuse or low voltage circuit breaker. Not an, maybe it looks complicated, it's not so complicated. Just drawing, chart drawing skills. What I need to do, what you need is just chart drawing skills. And this is easiest version. Actually, this one is easy. Future version are more complex. No, you have. Stupid system. Talk to me. Machine, please. Do we have someone online?